Alright, so in this video we are going to find all the isomers, octahedral isomers of the complex MA3B2C. So M is some central atom, usually a transition metal, and A, B, and C are unique monodentate ligands. Okay, so the way that we've been doing these problems, and if you look at any of the other videos on this section, we look at trans pairs. So this is a systematic way that I like to do this. And we have 6 ligands, so we're going to have 3 trans pairs. So we're keeping track of pairs of ligands that are across from one another. And to systematically do this, we do it alphabetically. So we look at AA, that will be the first trans pair in the most alphabetically advanced first place. Okay, so AA are going to be across from one another. And then next, to keep things alphabetically, is going to be AB. And once we have those two trans pairs defined, that forces the third trans pairs to do BC. And the rule I'm going to follow on this is I'm always going to write AB as AB. I'm never going to write it as BA because that would be reverse alphabetical order. So, BA and AB, that's the same thing. So I don't want to write it that way and get confused and think that it's actually something different. And so BC would always be written BC, not CB. AC, it's not going to be written CA. Okay, as another example. So anyway, that's one unique structure. And then I just continue in this manner and have as alphabetical of a manner as I can without being redundant. And we go through this systematically and cross out any redundancies. So we have AA again. We already did AB. That's the most alphabetical order we can be, but the next highest alphabetical order would be AC. And once I have those two defined, that forces the last one to be BB, and that is different than above. So I try again. AA, I've already done AC. I can't do AD, there's no D here. So that forces me to go into Bs. I can't write BA because that's the same as AB. I can write BB though, right? That would be the next. But when I write BB, that then forces my last one to be AC, and that is just what I wrote above, so that's not unique. I'm going to try AA again, and now I would be not BB, but alphabetically next would be BC. But that forces me to have my third one being AB, which is the exact same thing as what I wrote the first time, except the second and third trans pairs were flipped in the order that I presented them. So that's done. So I did AABC, that's the end of the line. I can't do AACA because that's just AC. Okay. So now instead of starting with AA, I'm going to start with AB. And so again, keeping this alphabetically, if I do AA, I'm on my ABs now. If I on AA, well, that is just the same as above. It forces me to have BC. If I do AB, I could do AB again, right? Because I have two B's. That would force this to be AC, and that's actually unique. Okay, so we uncovered a unique one. And then I keep going. AB, after AB is going to be AC. Well, that gets me AB, I just wrote in different order. AB, AC, I can't do AD. There's no D, so now I'm at BA. Well, that's reverse alphabetical order, so it's not allowed. So I can't do BB because I only have two B's, and that would be using three of them. So I could do BC, and that would force this to be AA, but I already wrote that up top in a different order, so that's no good. And now I've reached the end of the line at BC. So I've done all the ABs. Now I can do AC. Well, I can do AC, and the highest alphabetical one would be AA. That forces this to be BB. That's the same as what I wrote the second time. ACAB, okay, and that would force this to be AB, but I already have that. Here's the third one that I wrote. And then we could do AC, and we can't do BA because that's reverse alphabetical order, but we could do B, but that forces this to be AA, which is the same as our second one. And at this point, I'm done with the ACs actually, because if I try to do AC, I can't do BC because I only have one C. And so I'm done. Okay. So I'm done with all my AAs. I wrote AA, starting with AA I tried starting with AB, I tried starting with AC. Now I don't want to do BA, right? Because that's having a pair in reverse alphabetical order, but I could try starting with BB. If I start with BB, my first one's going to be AA alphabetically. Um, but if I do that, that forces this to be AC, and we already have that right here as our second one. Okay, so that's no good. If I do BB and then A, can't do AB, but AC, that gets me AA again. So I already have that. That's just what I wrote again. And then other than that, I'm pretty much done with the BBs. And so my last one is to start with BC, okay, and then AA, and that would force me to have AB. Well, that's my first one. And then I could do BC and AB. That gets me AA. I already just wrote that. So, you start getting this deep in the alphabet, you're always going to have redundancies. And you'll sort of start to see patterns. But if you really want to make sure that you're doing this correctly, just go through all of them systematically like I'm doing. BC, AB, I can't do AC because I only have one C. So I'm done with of my BCs, the one starting with A. So then I can't do BA, right? Because that's reverse. I can't do BB. And so I am done. And so at the end of the day, I only have three isomers. So let's label those. 1, 2, and 3. And now we can actually draw these, right? So out of the first one, I have an AA trans pair. So A and A are going to be across from one another. I have A and B being across from one another, right? A is pointing to the right and towards the front. B with the dash pointing to the back, to the left. And then I have BC. Okay. That was my third trans pair. So that's structure 1. Let's draw out structure 2. AA, again, trans to one another. But now we have A and C across from one another. And now, where I put these doesn't matter. I could put my AA here, my AC there, and there'll be some rotation, some symmetry element that would interconvert those. All right. And then I have my BB that's trans to one another. And lastly, I have structure 3. I have AB trans from one another. I have A and B trans from one another, second pair. And then I have A and C trans from one another. And so these are the three isomers that we have. As far as I know, these don't have like unique names, but we can ask the question, are these chiral? And so in order to do that, we look at mirror planes. We can see with structure, uh, we can see with structure 1 that we have a mirror plane that contains this sort of horizontal plane. Contains the metal, B, A, and C. And A at the top is looking at another A at the bottom. And so that is a mirror plane. And because that is a mirror plane, then so this structure is achiral, so not chiral. For the second structure, we also have the same mirror plane. there's potentially multiple mirror planes, but you only have to find one mirror plane in order to show that the molecule is not chiral. If you can't find a mirror plane for any of these octahedral examples, the molecule will be chiral. So we see the same sort of thing. It's not chiral, so we only have um, one. There's no enantiomers here for these two structures. Okay, and for this molecule, we also have a mirror plane. And the way that this mirror plane works is that it contains M, A, and C. And so it's a little difficult to draw here, but it is cutting through A and B and B. So B is looking at itself in the mirror, and A is looking at itself in the mirror. And so this is also achiral. Sometimes it can be useful to redraw the molecule in a different orientation to see that a little more clearly with these diagonal type mirror planes. But nonetheless, we do have three isomers here, and none of them are chiral. Okay, so in the other videos, we'll do other examples where there's even more isomers because there's more number of unique ligands that we have.